All right, 4.2 video notes, angle relationships in triangles. We're going to be focused on triangles pretty much all of chapter 4 and all of chapter 5, so we're going to know everything about triangles inside and out. Chapter 4 is where we get into quite a few proofs of triangles and trying to prove that two triangles are congruent. So I'm going to start introducing some proof. I'm going to give you the theorems, and then we're going to actually prove why the theorem is true. Just so we start getting a feel of the flow of the proof. So our objective today, we should be able to, at the end of this, find measures and apply theorems about interior, inside, and exterior, outside, angles and triangles. So I'm just going to kind of put that down there. This is inside, and this is outside for interior and exterior. All right, so let's jump into our first theorem here, and then we're going to do a proof of it. I've already alluded to this in chapter 1. We just officially haven't given it a name. It's important to know the names of the theorems because you can use the name in the proof. So the triangle sum, that means triangle, sum means addition. So we're basically referring to the angles. So the sum of the angles in a triangle, the sum of the angles is 180 degrees. All triangles add up to 180 degrees. So I'm going to prove this to you now instead of just saying, hey, take my word for it. We're going to actually prove it using some theorems that we've already done before. So I'm going to just draw a picture here. And we're going to label these angles angle 1, angle 2, and angle 3. And we're going to go ahead and we're going to get started kind of working through this guy. So let's do this. The first thing, this proof's a little tougher because the first thing I'm going to do in this proof is I'm going to draw in my own line. And actually let me put in some letters here. We're going to call this angle A, and we're going to call this angle B, and we'll call that angle C. All right. I'm going to draw in my own line, which I totally can do, and I'm going to make sure that this line is parallel to AB. So let's just put a point on this line, and I'm going to draw a line that's parallel to AB, which there's no harm in that. I can do that if I want to. So let's just write this off to the side, and we're not going to make this proof super formal, but we're going to say that line CD is parallel to line AB, okay? And we're given that, okay? And it's an auxiliary, an aux line. All right, so if I have that, I'm going to now add a few more angles in here. I'm going to call this angle 4 and this angle 5. And I'm going to use some information that we know. So I think from chapter 3, it's okay for me to say that angle 2 and angle 4 are congruent. So I think I have enough firepower to say angle 1 is congruent to angle 4. And what's my reasoning for that? Well, if I have parallel lines, these two angles form a special pair. They are alternate interior angles. So the alternate interior angle theorem. We had a theorem that said if two angles were alternate interior, then they had to be congruent to each other. So I know those two angles are equal. I'm going to use the same idea to say that angle 3 and angle 5 also have to be congruent. So angle 3 is also congruent to angle 5 by the same thing. Now if I wanted to, I could have wrote the two statements on the same line. I could have put this one right next to this one here and just used one justification. But I went ahead and just wrote it out separately. All right. So remember from back in the last chapter, these are my reasons or my justifications. These are my statements. And now I'm going to also use a fact because I got to somehow prove that they add up to 180. So how in the world can I bring 180 into this problem? Well, something that we know from before. I think I know for sure that the measure of angle 1 plus the measure of angle 4 plus the measure of angle, and hold on a second, I see right up here in my proof I made a mistake. That should have been angle 2. Angle 2 is congruent to angle 4. I'm sorry. So angle 1 plus angle 4 plus the measure of angle 5, that equals 180. Well, how do I know that 4 plus 1 plus 5 equals 180? And that's because they form a straight line. All right? Those angles form a straight line in there. I can't really say linear pairs, but I could use something like definition of a straight line. All right, the definition of a straight line is a line that's 180 degrees. Now what I'm going to do, I'm going to use an algebra property here. I'm going to use substitution. If you notice up above, I have angle 2 is congruent to angle 4. So wherever I see one or the other, I can replace it. So I'm going to substitute the measure of angle 4 here with the measure of angle 2 because they're equal to each other. I'm also going to substitute angle 3 and 5 for each other. And angle 1 I'm just going to leave alone. And look what I have now. I have the measure of angle 1, which is this angle, plus the measure of angle 2, plus the measure of angle 3, adds up to 180. And I accomplished that by substitution. So using some prior knowledge about alternate interior angles and straight lines add up to 180, I could use a little substitution move to prove, I'm done, I've just proven that this fact right here, the sum of the angles in any triangle add up to 180 degrees. So there are other proofs, there's other ways to do that, but that's one way to do it that's pretty straightforward. And the whole key there was I was able to draw in this auxiliary line to get parallel lines. That was extremely helpful. All right, let's move on down and let's actually apply this theorem. So to apply the theorem, this is going to go kind of quickly. I have a triangle where my angles are 47 and 67. So far I am looking at 114 degrees. And I need to find this angle right here. So basically I'm just going to do 180, take away 114, and I believe the answer is 66 degrees. So pretty straightforward. If I give you two angles, you add them up and you subtract from 180. This next one's an algebra problem. It's a little tougher. I don't have any of the angles, but I do know that this plus that all add up to 180 degrees. Now I could write all that out, which would be a lot of writing. I'm just going to kind of add these up as I go. So let's combine like terms. We're going to add together. So the idea here is I know that angle R plus angle S plus angle T equals 180. Well, when I add up all three angles, I'm going to be adding 7x's plus 2x's, that's 9, plus 4x's, that's 13x's. And then when I do the numbers, I have a minus 13, a plus 9, and a plus 2. So that minus 13 and a plus 9 and a plus 2, I think that all comes out to be a negative 2. So there's my equation. 13x subtract 2 equals 180. I'm going to add 2 to both sides, which gives me 13x equals 182. And divide both sides by 13. And that's going to go in there looks like 14 times. X is 14. Now if I wanted to find all the missing angles, I could just go back now and substitute 14 in. So for instance, in this angle, 7 times 14 is 98. Take away 13, that's 85 degrees. If I do this one, 14 times 2 is 28. This would be 30 degrees. And if I plug it in over here, 4 14s is 56. Add 9 to that. 56 plus 9 is 65. And if I did this right, the three angles should add up to 180, which I believe they do. So I always can see if I did it right by plugging the x back in and making sure they add up to 180. All right, moving down here towards the bottom, we're going to introduce a new term here called a corollary. All right, definition of a corollary. A corollary is just a theorem that kind of falls out or follow or not of or follows from a previous theorem. So it doesn't need its whole new proof. It's kind of like, well, once you know one thing, it kind of makes something else be true also. And the first one is that in a right triangle, okay, in a right triangle, so let me draw that over here. In a right triangle, the acute angles are complementary or equals 90 degrees. So for instance, if you have a right triangle and I'm not sure what these two angles are, I don't really have to add them all up, because since this angle right here is 90 degrees, to get to 180, it's going to be true that x and y are going to have to add up to 90, which is the definition of complementary. So it's kind of nice when you have a right triangle and you know one of these two angles, you can just subtract from 90 to find the other one. You don't have to add them all up and get 180. You can, it's just a little bit extra time. Alright, and then we have a second corollary that follows from that, which I already talked about in 4.1. But if you have an equilateral triangle, okay, if you have an equilateral triangle, which basically meant that all three sides are the same and all three angles are the same, okay, if you have three equal angles and the whole triangle adds up to 180, 180 divided by 3 means 60 degrees. So basically, equilateral triangles, each angle individually is 60 degrees. That's going to be true for every single equilateral triangle out there. It'd be impossible for an equilateral triangle to have different angle measures. Alright, so moving on down to our next theorem. Our next theorem is called the exterior angle theorem. And this one's pretty important, because without this, some problems really can't be solved. Some you can kind of work around, but some you cannot. And so here's how this one goes, and there's a little vocabulary here. Exterior angle theorem. The exterior angle of a triangle is equal to the sum of the two, and then here's where some vocab comes in, remote or far away interior angles. Now, the words don't really mean a whole lot, but I think a picture will help. So the outside angle of a triangle is equal to the sum, the addition, of the two far away interior angles. So for instance, let's just say we have a triangle here, and we extend one of the sides out further. So as far as our vocabulary goes, let me first label these angles. Let's call this number 1, number 2, number 3, and angle number 4. So just for vocab purposes, angle 4 is the exterior angle because it's on the outside of the triangle. So we have three interior angles, 1, 2, and 3. So 1, 2, and 3 are interior, inside. But in relationship to angle 4, which he's the guy that this theorem is about, in relationship to angle 4, the two far away interiors, 1 and 2, are remote interior. Alright, so this theorem is going to basically tie in 1, 4, and 2. We already know the relationship between 4 and 3. 4 and 3 have to form a straight line, and we're going to use that in our proof. Alright, so let's go ahead and try to prove this theorem. And so the theorem basically says the exterior angle, so we're trying to say that the measure of angle, what I want to accomplish here at the bottom is the measure of angle 4 is equal to the sum of measure of angle 1 plus the measure of angle 2. That's what I wanted. That would be this up here in words down below. The outside angle is equal to the sum of the two insides. Well, let's get after this and see if we can make it happen. So there's two facts looking at the picture I can use from previous theorems. Fact number 1 is let's see here. the measure of angle 3 plus the measure of angle 4, all right, these two angles right here, has to equal 180 degrees, all right? And how do we know that? Well, we know that because they form a straight line. They are a linear pair. So that's my justification. If you form a straight line, you have to 180. So that's a true statement. Now I also know here that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 all equal 180. And we just did that on the front page of these notes because the triangle sum theorem. All triangles add up to 180, and we've proven that already. So we can use it now. Now if I look up above and I look at what I just said, we have the measure of angle 3 plus 4 is 180. But then we have the measure of angle 3 plus these two guys are 180. So basically this and these have to be the exact same. And I can do a couple different ways. If I really wanted to do this correctly, since both equations equal 180, I can set the left-hand sides equal to each other. This is kind of long and drawn out, but I'm going to do it. The measure of angle 3 plus the measure of angle 4, that's the top equation, must equal the bottom equation. Okay. Why? Because I used substitution. I basically rewrote the top equation, but I replaced 180 on the right-hand side with 1 plus 2 plus 3. Now I can use some algebra. I can now say that the measure of angle 4 equals the measure of angle 1 plus the measure of angle 2. And how did I do that? Well, if you notice, what did I do from the line up above to get to the line below? I just subtracted the measure of angle 3 from both sides. So I used the subtraction property of equality. I subtracted the measure of angle 3 from both sides, and I got exactly what I needed to prove this. Now, I don't expect you to completely understand and follow those proofs just yet, but at least I'm starting to plant the seed of the flow of how you justify and go from one step to the next to the next. All right, there is another theorem here that falls out called the third angle theorem. And the third angle theorem is nothing too really exciting, but it just says that if two angles in one triangle are congruent to two angles in another, then what you can conclude is the third angles are equal. And I'm going to just kind of wait and talk about this as it comes up in a problem. But if you have two angles in one equal to two angles in another, then the third angles are going to be congruent as well. All right, let's actually get down and solve a couple of these exterior angle problems. So looking at this problem here, we're trying to find this exterior angle. So let's use the theorem. The outside angle, the exterior, is supposed to equal the sum of the remote interior. Well, that outside angle, question mark, should equal the sum of the two outside ones, 57 plus 66, which I believe shakes out to be, oh, what's that, 110 and 13, 123? 123 degrees. Now, I could check myself, and I honestly really didn't need the exterior angle theorem for this one. I could have just started and found this interior angle because I had 2 out of 3. Those two add up to 113, and when I subtract from 180, that's going to make this angle 67. But then when I come back and want to make a straight line, they have to add up to 180. So then I'm going to do 180, take away the 67, and I come right back to where I started with the 113. So I could have got around that one without using the exterior angle theorem, although it's faster. So final question here. This one we kind of need the exterior angle. So I'm going to set this one up using the theorem. So again, the exterior angle is the remote interior plus the other remote interior. That's my initial setup. So I'm just going to substitute in. So the outside angle is equal to, well, these are the two remote interiors. 69 plus 4x plus 12, and really the geometry is over. Now we're just solving for algebra. So I got 11x plus 1 equals, on this side I'm going to combine some like terms and get, what's that, 79, 81 plus 4x. Now I can start attacking both sides. I'm going to minus the 4x and minus the 4x, and that's going to give me 7x plus 11 is 81, and to get x by itself, subtract the 11 from both sides. That gives me 7x equals 70, and this one works out pretty nice. Divide both sides by 7, and I get x equals 10. Now I may want to plug that back in, make sure it works. So sticking x back in, 11 times 10 is 110, plus 11 more, that's 121. And sticking 10 in this equation, that's 40 plus 12, that's 52. So I have 52, 69. Let's just check that out. And we are money, 121 and 121. Alright, so that's basically the notes on 4.2. I will see you tomorrow to get started on the practice. See you.